plus the number of bits in the target fingerprint minus the number of bits in common. And I have to figure out how to say got it on the screen. Mouse. Sorry. Got it. Okay. So the Tanimoto we all know became popular in cheminformatics in the mid-'80s. Peter Willett in the group there at Sheffield identified this as a good way of doing similarity based off of the substructure screens back then. In fact, Willett even describes how shortly after the paper came out, someone said, hey, we read the paper, it was Friday afternoon, we went ahead and implemented it, by the end of the day it was working. So let's take us back to the 1980s. Everybody's got the Mac system on their machines, which already has substructure keys based off the Mac keys. Of course, we don't have that anymore. So I'm going to use ChemFPs, that's the program I've been working on, interface to the RD kit to generate the Max keys for Kimball 30 and make a text file output, which is header, followed by hex-encoded fingerprints and the IDs, simple text format. And okay, we're actually in 2022. I'm going to use Python 2.10 and write a similarity search program for that. I'm using 3.10 because if I use a fingerprint as an integer, then I can use the bitwise operation inside of ChemFP, and 3.10, Python 3.10 added a bit count, which is the number of on bits inside of the integer. So with these few lines of code here, I can show that caffeine and theobromine for the Max keys have very similar 0.96 or so similarity. Then I can easily take that and turn it into a similarity search program by opening the file, skip the header lines, decode the integer, do the bit of math here in the orange to get the Tanimoto score, and if it's greater than 0.5, save the score, the identifiers, sort them, and then sort from highest to lowest, and see that there's a number of structures which are similar to caffeine inside of Kimball 30. Now, however, to make this go fast is not so easy. You're not going to do this in just a couple of 15 minutes or so. So to start off with, why do you want things to go fast? You can think about things like you can get the feedback faster, you can explore more science, discover more things. There's also more operations concerns, like you could put the substructure search, similarity search on your web server machine, so your web server can right away display results instead of have a dedicated machine.
Sorry,
elsewhere.
Yes. Are you still on the slide Tanimoto similarity, or is it a different one?
No, I have gone forward.
Okay, because it didn't change here for some reason.
Screen sharing is paused. I'm now screen sharing.
I go fast. I think now it seems to be right.
Well, I'm gonna. Do you see it here? Yeah,
no, it's fine. Yeah.
Okay, so we're here, and then they had the message to say I got to press the OK button to record, and that's the thing that's got a bit messed up. So we'll do it this way. So FBS format, text format. You can do Tanimotos very easily in Python. You can do a search program in Python. In 2.5 seconds, search 2 million structures in about a dozen lines of Python code. So that's great, but you really want things to go fast. For some technical reasons, but also emotional reasons. You'd be surprised how much software is developed for emotional reasons. Part of my interest in making this, developing ChemFP was reading all these papers talking about, here's a new way to do similarity search faster. And I look at them and their baseline reference is quite slow. So I wanted to raise the baseline so that I could understand how these papers are actually useful. Now, there's many ways to make things go fast. One is to, well, don't use Python. Python's a pretty slow language. In fact, that same search in ChemFP, which is using C extensions, is about 1,000 times faster. As the number of ways to make it go faster, one is to avoid text. So in ChemFP, there's also a binary file format, which is much faster to load. You want to do things like make sure that your fingerprint type matches the actual representation that you want. The representation matches the data you have. So even though it was nice and easy to use Python integers, turns out they use 30-bit words inside of their integers. So it's a bit extra space. On the other hand, it was easy to use. But the downside of that easy to use is these operations, the bitwise intersection, bitwise ORs, those are making temporary integers, which are then thrown away because all it cares about the bit count. If I can push all this information down into C, I can make it go faster. The result is, now there's no way to get the number of bits that are on the Python byte string, so I have one called byte Tanimoto here. But the end result is I can, even at Python level, go a bit faster than I did before by working on byte strings with this program, with this code in C. Now, this bit of code that's in C, what it's doing is saying, get each of the words, in this case, it's 8 bits at a time, that are inside the 2 fingerprints, count the number of bits in common, count the number of bits in the intersection, and get the result. Now, I use this word here called pop count. That's the term that's used often in the field for population count, the number of 1 bits in a word. And a simple way to do it is to have a lookup table. If you have an 8-bit value, then there's only 256 possible ways values you can have. So you can just have a table of lookups. You have the value of 5, that's 101 in binary, that's a pop count of 2. But there are a lot of algorithms people have developed over the years to be able to make this go fast. And on modern machines, you even have built-in instruction. So the processor has an actual pop count instruction that works on a word, usually 64-bit word, to give the results in basically one operation. It's so good that even if you're using max keys, which aren't exactly a multiple of 64 bits, most fingerprints are a multiple of 64 bits, you just add a few extra zeros at the end because you want to use this instruction to go fast. You don't want to save that much space, that little bit of space. Another programming technique is what's called loop unrolling. If you really know that you're going to do max keys, scientifically speaking, don't use max keys, but this is an example. If you're using max keys, you've only got a couple of pop count operations doing some summation to do it. Don't do a loop because the loop has overhead. But then another way to do it is to avoid some of these pop counts entirely. In this previous slide, I had 2 sets of pop counts. But if I have a query, I know the pop count, and the targets are usually pretty static, so I can pre-compute their pop counts. So the query has pop count of A, target has a pop count of B. I can reduce the calculation to just compute the intersection of pop count and get the result with a bit of mathematics. That about doubles the performance. And then once you do that, if you can then sort fingerprints, then you can group everything into bins so that all the fingerprints, well, the one possible fingerprint with 0-bit set, the fingerprints 1-bit set, and so on in order. And that way you can simplify the code because down here at the bottom, the score is now C over the shared common A plus B part minus C. Now, of course, you're not going to do this in Python. You'll do this in C or Julia or Rust or whichever compiled language you prefer. But you'll find that even when you get down to that level, you start having problems because the C function call overhead starts taking time. So I'm using a tool called Compiler Explorer. You can go to the URL and see this. And it's showing you on the left-hand side the C code, and on the right-hand side the assembly code that maps to. And you can see it's very short assembly code, but about a third of it is just on the overhead of how to set up a function call, do the function call, and return the value. And a compiler will, if it knows that you're really only going to use this function, it will try to inline it, which means it won't even do the function call at all. I had to disable inlining here. But of course, if you have a general purpose tool, you're going to have either a general purpose function call, or you have to specialize all of your operations for the different fingerprint lengths you do. Another thing to do is avoid the division entirely. In many cases, like if you're only looking for very close similarities, 0.95 or so, you can replace 9.95 is the same as negative over 20. So you might do a fast test to say to reject all these mismatches and do a slow division test. Because divisions, even on a modern machine, is still pretty slow compared to other operations. Now, there are some alternatives here that I'm not going to discuss. In ChemFP, what I do is I realize you can rewrite the equation as the intersection pop count must be greater than or equal to a certain threshold. And that threshold is constant for a given A, B, and threshold value. So the bit of math that you have, if I have a little question mark over it, is that. And the question mark is there because you have to do a little tricks because math, the way the computers do math means you have some rounding issues you have to take care of. But the end result is you do the intersection, and then you do a test, and that tells you if it passes or not. So all you're doing is the intersection over and over and over again when you're doing the search. And then in the ChemFP, what I do is I store all the fingerprints, what I call an arena, fingerprints in order, and there's an index for each pop count to the start of the first fingerprint with that pop count. So I can quickly figure out that all the pop counts with all the fingerprints with, say, 10-bit set are from here to here. Now, at this point, you're going quite fast, and you start to realize that pop count isn't actually as fast as you think it might be. So yes, I said you could do 1 instruction per second for pop count, but then you do the math, say it's a 2 gigahertz processor to make it the math easier, then that's still At minimum, it takes you 16 nanoseconds to do the fingerprint. Now, a processor doesn't just execute one instruction at a time. It has multiple what are called instruction ports. So it's trying to figure out, oh, I can do this now, send it here. I can do this one, send it here, work on things in parallel, and then give you the result. But since only one execution port on Intel CPUs can do a pop count, this is going to be your minimum time for a 248-bit fingerprint. Though if you're on AMD, AMD has 4 execution ports that have pop count support. I've never had access to one of those machines. But then a few years back, these people here pointed out a paper that you can use on Intel and AMD hardware. There's the AVX2 instruction set that operates on 256 bits at a time. It doesn't have pop count built in, but even though it's more instructions to do it, it's operating on bigger words and they can be done more in parallel to get even faster than what you would think. The built-in CPU does this as fast as possible, sort of thing. That's what QMFP has now to get even more performance out of it. But when you start now pushing the AVX2 and get all this working, then you find you have other problems because memory is actually pretty slow. If you were to ask memory for something, it goes way out there, it comes back about 100 nanoseconds just to get something. But I told you only about 15 or so nanoseconds to be able to compute the Tanimoto, the pop cut intersection. So the processor would do a lot to figure out, load a whole page of memory at once, not just one fingerprint at once, and bring data in. But this is one of the few fingerprint search is one of the few cases, cases that I've personally experienced, where I can tell the processor, I'm going to need this in the future, get it for me so that when I get to that point, it's already in memory. And all of these add, all these add a little bit of performance here and there, but you keep, I guess, add them up in log space. You eventually get something that my original version of QMFP used these 8-bit lookup tables. And my current version now uses this inline prefetched AVX12, and it's 10, 11 times faster than the original version, only by changing how it's doing the pop count evaluation. So I look back at these papers and they talk about their algorithm is 3 times faster than the brute force search. And then it's like, but is it really appropriate now? If the brute force search is 10 times faster, can the other algorithms also be improved the same? So part of my goal on QMFP was just to have a good solid baseline to make people have papers I could trust better. Right. So back to the software. A few years back, the Swamidasan and Baldi pointed out that you can prune some of the search space. If your query comes in, has a 100-bit set, say, and your threshold is something really nice, like say 0.9, then you have a very small narrow range of target fingerprints you can look at. And since we've already sorted by pop count, we can just say start here and start in here instead of starting here and ending all the way over here. The paper showed an example of how that might work. Their paper uses 0.9, but in real life, you're going to look at, say, 0.4, so for Morgan fingerprints, ECFP-like fingerprints. So this looks pretty good. It's like I can chop a lot of space, but of course, in real fingerprints, a lot of them are going to be similar number of bits in the fingerprint. So for Kimball 30, use the Morgan 2 fingerprints. If your query has 70-bit set, there's you're printing about 3% of space. So it's not very useful. It's nice. Again, these extra few percents, they multiply together. They give you overall better performance. But the paper also pointed out that this can be used for nearest neighbor search, because if you have a query come in, and if there's a high similarity scoring fingerprint that's already in your database or your set, then they're likely to have very similar number of bits set. So if it's identical, they're going to have the same thing and be in the same bin. Otherwise, you start searching bins outward in a way that they describe in the paper to preferentially order your search to find nearest neighbors. And if you find nearest neighbors, each time you find enough neighbors, raise the threshold, you raise the threshold. And so a few years ago in my QMFP paper, I did some analysis of, for different analyses, doing a nearest neighbor and doing a straight threshold search. On the left-hand side, you see this is in milliseconds to search Kimball. Doing nearest neighbor search, the queries are taken from the data set. So the k equals 2 is actually a nearest neighbor search. You can get over twice as fast because you're putting enough, because the search ordering is helping you prune space. If you have enough neighbors, you have to evaluate the entire space, and that takes about 28 or so milliseconds. And the same with threshold. The threshold is high enough, you can go several times faster than if you have to search all space linearly. In fact, they even pointed out, and I confirmed, that the nearest neighbor search is sublinear. So if you're looking for the nearest neighbor in, say you're using the Morgan fingerprints, it doesn't order in the number of fingerprints, it's actually 0.8 in the number of fingerprints. So that's nicer if you're working for large data sets. You do get a little bit of extra advantage for nearest neighbor search. Another common way to make things faster is to parallelize them. In ChemFP, I use OpenMP, but because it's using these instructions, using these pop-cut evaluations, they're so quick, and the amount of calculations that are being done are so short, I'm actually running into memory I/O problems. And I'm not going to get into the details I give here because next page I'm going to show you that if you've got stuff in memory, you have to bring all these fingerprints into memory, all maybe 97% of your fingerprints into memory. You have a memory channel. All the stuff is feeding to your processor. And if that's 25 gigabits per second, you do the math, that's about 10 nanoseconds per fingerprint, which is about the same time it takes to do that evaluation of the pop count intersection. So you basically can have one CPU consuming one memory channel, and that kind of sets some hard limits of how much faster you can go. Now machines nowadays can't have multiple memory channels, so you can get better than this if you have multiple cores. But it's still a rough guideline of you're just starting to get to the point where it's really you have to worry about the machine architecture to know what you can do. And one of the ways that's more sophisticated than what I do is in this paper below. Now, before I get to diversity selection, a couple last things. If you're willing to throw away some accuracy, you can use approximate methods. That red arrow points to a ChemFP, the pop count version of ChemFP, but not the AVX2 one. And the left-hand side is in log space. So if you will be a little bit less accurate, you can get an order of magnitude faster or two in your searches. And if you're using really sparse fingerprints, less than about 0.2 or so, there are other techniques. Sorry, 0.02, 2%, 1 bits versus 0 bits. Then you should look to sparse methods. This is what I'm showing here is fingerprint density on the bottom. And then on the side, I'm showing the ratio between ChemFP performance and a paper that came out for doing sparse fingerprint searches. And you can see that around 2% is a point where for different queries and different fingerprint types, sometimes ChemFP is better than RISC, and sometimes it's the other way around. All right, so that was the similarity search. Now the question is can we apply these methods from a similarity search to diversity selection? And diversity means a lot of things, and different things to different people. There are a number of approaches. The two main ones that I found are max-min and sphere exclusion. Both of them are available in the RD kit, which is probably what most people use, and those are developed by Roger Sale. The max-min algorithm says that you want to pick say 1,000 1,000 very dissimilar compounds inside of your data set, and you don't want to compute the full n-squared matrix because that takes a while. Even if you with a high performance, it's still an n-squared operation or n-squared or 1 to the 8, 1.8 evaluation. So the maximum is an approximate solution to be able to get you those quickly without evaluating the full matrix. The idea is you have one or more initial fingerprints, and of the remaining fingerprints, find the one that's most dissimilar. And dissimilar for my talk means 1 minus Tanimoto. There are other metrics people use too. Add it to the picks, and then do the same thing again, and the same thing again, repeat until done. A few years back, Roger Sale developed an improved implementation of this, which is in the RD kit. Now, this is not the method that is in the RD kit or the Roger Sale developed. It's my reinterpretation of it in the way I'm about to describe for my algorithm, which is you take that initial pick and then set up a queue, a priority queue with a depth of 0 for all of the remaining fingerprints and the score to this initial pick. It's priority queue, so the smallest score, the lowest Tanimoto is always first. Pop that off the queue, compare it to the picks, because you know there's a certain depth inside the picks. Keep on trying the remaining picks until you reach the end. If you reach the end, that's a new pick. Otherwise, whoops, there's a new the summation score is too high. Stick it in, try again. Keep trying again. Now, there's some obvious improvements on that. They're using the same techniques of faster Tanimoto search, faster pop count intersections, and so on. The result, it turns out to be about 2 or 3 times faster. And one thing I found out is, I first found out my code was like 8 times faster. Like, wow, I'm so much faster. And if you sort all the fingerprints by pop count, which is what I do natively inside of ChemFP, then RD kit's max-min is also faster. So you also have to be careful about how you do these tests. Anyway, one of the things that you can do with max-min is what I'm calling candidates versus references. So if you want to, if you're Kimball and you want to buy some compounds to improve your diversity, so you have your candidates from E molecules and your references, which are the Kimball data sets, you want to pick ones that are diverse from what you already have. You could treat this as one big data set where the initial picks are your Kimball ones, and then you have the rest of it. And this is what the implementation in RDKit does. Alternatively, you could break it apart into two parts, because you could say, find the nearest neighbor in your references, the things you have. And then once you do that, then go through the picks. So it's basically taking that same thing, split it into two parts, working through references, and then work through picks. So it looks more complicated, but the reason why this is useful is because you can now look at this as the nearest neighbor search, doing that max-min bit-bound search, doing the bit-bound search, through the tree, finding more and more appropriate fingerprints, searching through the searching through the references in an order that optimizes a good match. And so that way you quickly set a high threshold and prune out a lot of space, giving you, in my timings so far, about a 30-fold improvement in performance for that task. Now, one of the issues when you're doing max min is doing the initial pick. You can pick it at random, you can pick the first one. I wanted to make it so you always pick the globally most dissimilar structure. And by the way, as a rule of thumb, you can probably pick the smallest pop count, because what I found is the smallest pop count is usually the one that's most diverse. And I used a sweep approach. So sweep means you've got a candidate fingerprint, and you do its similarity with everything else that's in your data set. Now you know what its the similarity score is, and you can set a bound on everybody else's similarity scores. So you can have a scoreboard here. Do 50 of these at random just to initialize a priority queue, and do the same idea, pop it off, see if it's the smallest. If it is, then you've got it, you can use it. Otherwise, reevaluate, do a sweep, and keep on going. So this can give you the globally minimum fingerprint in, it's a bit longer than max min for the globally minimum fingerprint, but it does give you the minimum fingerprint within a few seconds or maybe a few minutes for a large data set. And you could then keep on the process. You could find now globally minimum across all your fingerprints if you keep on using the priority queue. What I found when I did that was there's kind of no point. It takes, what is it, 3 hours to get to 0.4 similarity, and that's the time when you could have just done a full n-squared evaluation. So if you wanted a handful, the first few dozen or so, most diverse compounds would use this, which you would do if you wanted to seed max min. And the last technique that people often do for diversity selection is a sphere exclusion. So that was one where you say, pick a fingerprint at random, then ignore stuff around it. Just take out the sphere, take all the fingerprints around it, pull it out, and then do the same thing, and do the same thing. And that gives you kind of a biased distribution, more scattered distribution instead of a possibly clumpy distribution of points of your intersampling. And you can apply the same methods for faster tiny modal search, bit bounds, and so on, giving you, again, about a 3 or 4-fold performance increase. And then there's a method called directed sphere exclusion. And that says, instead of picking points at random, have some sort of ranking function and use the fingerprint that's the highest rank or the best rank. In the Dicey paper, it's towards a set of compounds that you're interested in. But you can also, as Roger Seal pointed out, choose maybe of the fingerprints that are left, use the one that's cheapest to acquire. Yeah. Now, if you start working, well, I described that. So if you start working with max min, you'll find out that it starts off with a bunch of junk. And so make sure you filter out your inappropriate structures first. Now, one of the things to do is to say, well, maybe I'm working this chemistry space, so find everything that's, I don't know, 0.3 or so or lower, and discard that. And I realize that there needs to be an operation that says, I want to know, does there exist at least one fingerprint at a certain threshold? So not all fingerprints at a certain threshold, or not the nearest neighbor, but just, is there one, so that you can discard the rest? And so that's probably something I'll be working on in the future. And lastly, talking about diversity selection is, examples I gave are for the millions, tens of millions of structures. Now, if you want to do diversity selection from billions, these don't scale. You can't get it to go very well unless you spend a lot of time. And the problem is these are all single-threaded operations. If you really wanted a big calculation, you could do that similarity search across 1,000 CPUs and break things up. But these algorithms that I'm describing, the max min, are all single-threaded. So what you might be able to do, and this is something I want to research, is break up the large set, do the max min of a subset of another subset, merge those together and do maximum again. Then I'm curious on how that would work. Anyway, so that's the stuff I've been working on for the last, that's basically my COVID project was developing these methods for diversity search. And I wanted to give big thanks to Roger Sale because he is the one who explained how these methods, not only how do they work, but also kind of how you'd apply them for doing science. I also thank the RDKit developers for including these algorithms inside of RDKit so I can study them and understand how they work. And lastly, to Jakob Gunera, who helped me understand some more of how to think about the idea of candidates and references. And lastly, a bit of advertisement. These are all the stuff I described here is in ChemFP, or I should say will be in ChemFP 4.0, which is supposed to be out this weekend, at least by ICCS. With that, I'm done. If there's any questions. I can see applause, but I don't hear anything.
Great. Thanks a lot, Andrew. Certainly talk worthy of the Cheminformatics meeting. So any questions? Let's see. We'll have a look at the chat first. Okay, now that's the questions about the slides. Yeah, a copy of the slides. Andrew, is that okay if we put those online as well? Yeah, just send them over afterwards. I'll put that on.
I already sent you the URL.
Okay, very good. Thank you. Okay, excellent. Yeah, there's no scientific questions in the chat right now. From my perspective right now with generative models and virtual libraries, there's really, it's quite relevant, right? If you talk about nanoseconds, you might think that's very abstract, but it really matters if you have a virtual library, right? And 10 to the whatever, 9 compounds, yeah, that those speeds certainly do matter, right? So any questions from anyone? Sure, no, right. So let's see, I think.
How about now? Hello, Andrew.
Hello, I hear you now.
Okay. It's more of a comment. Okay. Sorry. Just as regards the billions, I don't think you really need an exact solution. If you can parallelize it and do some sort of selection, you know, one selection is really as good as another. So, you know, I wouldn't go out of your way to slow it down to get an exact solution. If you can speed it up and get a kind of inexact solution.
Are you talking about for the max min, or are you talking about from my heap sweep one that gives the globally diverse fingerprints?
Well, I would say for everything.
Okay. Well, the thing is if you want approximate solutions, then I think the easiest approach is to distribute. I mean, the easiest way to parallelize this is to have 1,000 machines running doing subsets, or working with the subsets and do the similarity search. Because the problem with these diversity selection ones is, yes, they give you the first diverse ones very quickly, but they're doing a whole bunch of moving memory around or looking at random access points in memory. And those are all about an order of magnitude slower than just getting the data pumped into the processor. So it's really a trade-off question about how many do you want, what you want to do with these fingerprints. If you want a large number of fingerprints, work within the n-squared matrix, even for large multi-millions of fingerprints. It's not that big.
Thanks.
Yeah, cheers, Andrew. Chris has a comment as well, no question.
Hi, can you hear me? I do not hear you.
Oh.
I hear someone in the background saying, do I hear you? Hi, can you hear me now?
Green. It's a green.
Hi there.
Hello.
Just following on from Noel's comment, really. I was just thinking, if you're trying to select 1,000 or more diverse compounds from a library of multi-billions, wouldn't it be just as good just to select a random selection?
Probably. The thing is I am mostly a software developer. So I can tell you how these algorithms work, but then when you come to the applications of it, I'm not so good at that. And when you're talking about thousands out of billions, then it's probably random works. Of course, you're still going to do the same filtering. But how many times, I don't know. This is a scientific question that I can't answer. I can develop the software for it.
Okay, great. Thanks a lot. Is there any other question online or here in the room? Yeah, there's nothing online. Great. And there's I'll bring you in touch with some people as well, Andrew, who actually have exactly problems of that type. Yeah. So thanks for giving the talk. It was excellent.
Okay.
Let's applaud Andrew
Thank you.
again. Thank you. Okay, very good. And we will come to our second speaker then, and that's Andrew Stolman. Hi, Andrew. Could you actually?
Hello.
Hello. Thanks for joining us. Can you try sharing a screen and see if that
Yes. You all can see the slideshow.
Yeah, looks good so far. Do you want to make that full screen as well?
It should be full screen.
Okay. Yeah.
Does it not appear full screen?
Now it is full
Okay.
screen. I think now it looks good. Great. I think we're ready to
Great.
start. Thanks.
Cool, thank you. Well, thank you all for having me. I'm really excited to speak here. My name is Andrew Stolman. I've been a software engineer at Katana Graph for the past year after doing my doctoral dissertation on graph algorithms. I'm a newcomer to this cheminformatics and automated drug discovery stuff. What I do know about and what I want to talk to you today about is large-scale graph computing and how that can help you with these cheminformatics workflows. So I just want to start off with thanks to all the people. This came out of a collaboration that we did with AbbVie. So I just want to thank all the people at Katana Graph, and Abixil, Brian Martin, Philip Hajduk, and Jennifer Van Camp for their expertise at AbbVie and helping us with this project. So let me start by explaining what are graphs. And these graphs are abstract mathematical objects which we use to model relationships among different entities. And what's powerful about graphs is that they're capable of representing heterogeneous data. You could have a lot of different entity types. So for a simple small graph, we can take a molecular structure and convert it to a graph representation, where each one of these atoms in the molecular structure becomes a node in the graph, and the bonds between the atoms become links in the graph, or what we normally call edges. And so that's basically what a graph is. You have a bunch of nodes and a bunch of edges, and you could have some properties on the nodes. We could even have much larger, more complex heterogeneous data sets represented as graphs. And I think one of the most exciting things for cheminformatics is the ability of these heterogeneous data sets to represent things at different scales. So we can, if you look at this like big heterogeneous scheme I have here on the right, we can have nodes that represent individual compounds at the smallest scale. This is just at the molecular level. And you can have those relationships to drugs and combinations of drugs and build up relationships to bigger things like genes and proteins, come up with associations to organism level effects, diseases, whatever kind of bad effects or good effects you want to know. How does it affect tissues? So it's possible using these graph data sets to make inferences from the very small scale up to the very large macro scale that we generally care more about. And so when we're talking about these large heterogeneous graphs, you need appropriate hardware infrastructure to deal with these gigantic data sets. And for graphs, we use some kind of distributed graph computation platform. This is the way ours works. So we developed a Katana graph. It's a client-server model. So you as the data scientists are sitting at your laptop writing a Python notebook or whatever, and you send your analytics and search queries to this server. And the server has a bunch of machines. Here I have it representing 2 machines. We have our whole graph, and it partitions the graph across hosts. So that host 1 has a piece of the graph, and host 2 has a different piece of the graph. And this server then runs whatever computation you've asked it to do and returns the result back to you. And there's a lot of engineering going into partitioning the graph, this distributed communication. But the whole point is we have an end-to-end platform that makes that a convenient black box for the user. And so once you have your data in a graph, I want to talk about the kinds of tasks that unlocks for you. And we think about it as three main areas. You can think about querying your database. So you have some known data set and you want to, explore things in that data set. And I'll come through some examples of cheminformatics querying we can do. And I'm going to kind of combine graph analytics and mining and machine learning into one thing in this talk. They're very related. This is what we want to do when we want to make inferences if the data is missing values, or we want to extrapolate further to other data sets. We enter the realm of analytics and machine learning. So let me show you a graph schema we actually have. I apologize for how blurry this image is. So this is what we've imported a number of graphs into a number of publicly available data sets into a graph representation. This picture is our Kemble 30 schema. And so every one of the dots you see here represents a different node type, and we have different edge types. I have zoomed in here a pretty interesting part of the graph just to show you what the structure is a little bit. So if you look at the bottom left here, what the node says is molecule dictionary. And then if you look at this orange node, this one is activities, and then the green node is assays, and then we have a path up to cell dictionary. So we're able to build these associations up from molecules to activities to assays to cell dictionaries, just from the Kemble data set, working our way up the hierarchy here. And in order to take advantage of these kinds of graph patterns, we use a graph query language. And the one that we implemented, Katana graph, is OpenCipher. This is the most popular graph query language to my knowledge. And it's a very simple query language that it looks a lot like SQL in some respects, but it's customized for graphs. And I want to show you a few example Cypher queries to give you a sense of how it works. So most Cypher queries have basically two parts. There's going to be some pattern part, which I have in the green box here, and then some function part, which I have in the red box here. You can see this pattern part. What I'm saying is I want the system to find all nodes of type compound. That's what the colon means, find type compound, where the edges of type has activity against, and the target is some specific target, where here I just gave it the name target. So what this part does is it finds all compounds which are known to have activity against a given target. It finds this pattern I've drawn at the bottom of the slide here. Just a simple node, edge, node, pattern. And then the function we're computing on this is just count how many times that pattern appears. So this very simply just for a given target counts how many compounds in our database have activity against this target. Very simple query. And we extended the OpenCipher standard with an RDKit implementation integration. But some of these are just straightforward, like wrapping the RDKit functions for Cypher. We have things like the find minimum common substructure, where you can give it a list of molecules and it'll output, the common substructures between those molecules. We implemented, you can call these varying fingerprinting methods from within RDKit. And we have the 4 of them here. You can compute the Tanimoto similarity between fingerprints. And then we did a little bit that was beyond what's implemented in the RDKit to speed up similarity search and substructure search. For similarity search, we implemented an indexing. So you would pre-run this indexing method on your graph. And the way it works is it's just a distributed min-hash locality sensitive hashing technique. This is a pretty straightforward, like off-the-shelf method in computer science for finding similar bit vectors. And it seems to work reasonably well in this domain. It distributes nicely, which we care about a lot, and it parallelizes nicely. We can throw a lot of threads at the problem. This example here on the lower left is just what the code looks like to do it on a batch. And here we print out, we looked up similarity for 3 molecules and printed out the first 5 results we got for the 3 query molecules. And here, just as a comparison for performance, we compared it to the PostgreSQL RDKit package, which is inherently single-threaded. And we're able to throw more silicon at the problem. So obviously we're faster, and we have this curve here that shows at different Tanimoto thresholds. The y-axis says how many times faster Katana was than Postgres. So it's the quotient of the runtimes of Postgres over Katana. And you can see that at 0.7, Tanimoto threshold of 0.7, Katana is 24 times faster than Postgres. For substructure search, we implemented a very simple indexing method. We needed something that would distribute well, that parallelized well, and we found this very simple method to work well. And we used the pattern fingerprints from the RDKit package. And what those pattern fingerprints do is that they just enumerate a bunch of subgraphs that might appear in a molecule. And if that subgraph appears in a given molecule, that molecule gets a 1 in that fingerprint position. And if it doesn't, then it gets a 0 in that fingerprint position. So we played around with a few methods on how to do this. And the fastest thing we found was you get all your pattern fingerprints. So every host is responsible for some chunk of the graph, some number of molecules. For all the molecules it's responsible for, it computes the pattern fingerprints, and it stores it in a table like this, where you can see each row here is a different pattern fingerprint in the table. Then what it does when we get a query molecule in, is it computes the pattern fingerprint for that query molecule. And it looks at each on bit in this query molecule, and it looks at how many molecules in the table set that on bit also. So here we can see that at position 0, the query molecule is on, and there are 2 molecules that also set position 0 to on. The other one that this query molecule sets to on is at position 2. And we can see that there's only 1 other molecule that sets position 2. So what we do is now we just do basically brute force computation on this smallest set. We return all the molecules in this column and do subgraph isomorphism. And when you're running, with 5 machines that all have 80 threads, turns out this is pretty fast. You just need some simple pruning to quickly cut down the search space, and parallelism will take you the rest of the way. And so this is admittedly less sophisticated than the substructure indexing that PostgreSQL has, but still, because we're able to parallelize better, we were able to get 7 times faster with 1,000 random query molecules on a single host. This is not even using multiple partitions. So let me show how you can now put these together with basic Cypher stuff and how this unlocks new computations we can do. So here's an example Cypher query that we worked on with Happy. What this match clause is saying, the pattern, is we just have a path. It's looking for paths where we're starting with a compound. Some of these names might make more sense to you guys. I don't know what a CID is. I have some sense of what an assay is, and then it ends at a gene. So we're looking for compounds that interact with genes. And if we're going to limit the ones we look at, we're going to limit the compounds we look at where they're canonical, where they're appear in this substructure search result. So here I've given it this smile string, and so it's only going to match these nodes for n, which contain this given compound as a substructure. And then we just return the name of the gene in this pattern and the count of how many compounds interacted with it. So in summary, what this query is computing is you're giving a specific substructure, and then for your whole data set, you're going to go through every gene in the graph, and this simple query goes through that gene and says, how many compounds in my data set have the given substructure and interact with the gene? And I also want to talk about how we go beyond querying, because querying is great, but it's only going to tell you stuff that's already in your data set. How do you infer new data? Because that's the point of drug discovery. People haven't discovered it yet. And so now that you have your data in a graph format, there's some basic graph machine learning tasks that are pretty easy to yank off the shelf and use here. Some basic graph machine learning tasks they'll talk about. So there's node classification and regression. We're trying to predict some label or value on each node in the graph. So here, predicting whether or not a given compound is toxic would be an example of node classification. And regression is just when you're trying to predict some continuous value rather than something discrete. So like here in this example one, we would like to infer whether compound A is toxic, and we have some interaction graph where we know the toxicity of some pre-labeled compounds. Another kind of machine learning task is where you're actually, for on graphs, is where you're actually trying to learn the graph topology. You're trying to discover, like, is there some edge? Like, it could be that if you have your cheminformatics graph, that you just have some unobserved interactions between compounds and targets. And so you want to predict which interactions have I not observed yet, are most likely to actually be real if we did the experiments. And this kind of problem falls under link prediction. So we entered this therapeutic data commons competition to help us develop machine learning methods for cheminformatics. And this competition, I believe it's 22 data sets. It's this ADMET group challenge: absorption, distribution, metabolism, excretion, and toxicity prediction tasks. And the goal of this competition is to give one model that does well on all 22 of these tasks. And some of these tasks below, they're all classification or regression tasks. So this HERG blockers, you want to predict whether a given drug will block HERG or not. This CACO2 one, you want to predict cell permeability here. This is a regression task. You're predicting a continuous value. And yeah, blood-brain barrier, this is another classification task where you're trying to classify drugs as to whether or not they'll penetrate the blood-brain barrier. And yeah, just a few more details. It's the competition, so they give us a fixed evaluation metric and the scaffold splits for the test data. So the existing methods for these kinds of problems, these classification and regression tasks on chemicals, break down into a few different methods. I would say the first and simplest are these fingerprint-based traditional machine learning methods, where they just use something like the RD kit to compute a fingerprint and feed this fingerprint into some machine learning method like a decision tree or a random forest, and use that to predict new instances. You can go into deep learning with a similar approach where you compute the fingerprint, and now all you're doing is feeding this fingerprint into a multi-layer perceptron neural network and to compute your function. More recently, there's been some look at how to incorporate graphs into these problems. And the main graph approach that you see is to convert so the data sets are generally a set of molecules. You convert the molecule into a graph, and then you feed that graph into a graph neural network, or a GNN, which is able to take, unlike the MLP, which only takes the fingerprints or some feature vector, the graph neural networks are able to take a feature vector and the topology of this graph that we built when doing its calculation. And yeah, you can think of this, I talked about on the last slide about node classification and regression. You can think about this approach as framing it as a graph classification or regression task. So just to give you a quick taxonomy of the methods that were already there. These are the fingerprint-based ML methods. These include like XGBoost, MLP, and the basic idea is you take a molecule, you convert it to a fingerprint and do machine learning there. For the other group of methods, you take a molecule and you convert it to a graph. And this covers methods like attentive FP, Grover, the attribute masking. So our method we called SimGCN. And we're able to leverage some of the LSH and querying stuff that I talked about before to come up with a new model. And we pose this instead of we want to use GNNs. We think they're powerful, but we want to pose this as a node classification regression task instead of a graph classification regression task like the other methods have. And the way we do that is we have our data set. We compute the fingerprints for all the molecules in our data set, and then we compute the similarity graph on top of it. where we add edges between molecules if their fingerprints are similar. And then we take this, and there's a couple of ways you could build a similarity graph. You could come up with a predefined Tanimoto threshold and say we're going to include all edges if the similarity is above the threshold, or you can build a k nearest neighbor graph where we say we're limiting it at k neighbors per vertex in the graph. It's which is better, kind of depends on the data set. And yeah, we're able to leverage LSH to quickly build this and querying to quickly build these similarity graphs. And this is a little bit more about what it looks like. First, what we do is we do the cipher query to get these similarities and the labels for the given target. We convert that to a graph. And then we feed this graph to the GNN. And the GNN is going to come up with embeddings, and then you can cluster and classify the embeddings. Each one of these dots in this graph would represent a different compound. And it turned out that this SimGCN one did pretty well. These slides might be a little bit out of date. I think we might have actually been passed on a couple of data sets since the time. But when we first submitted, we were the best on the most data sets. I believe, so yeah, on over a third of them, we were the best. And on the rest of the data sets, we weren't that bad. And in general, this is just, we don't know, like our group doesn't know anything about chemistry. We have definitely some domain experts like Katana, but I can say that for the people developing this model, we were a bunch of machine learning nerds. We're not chemistry people. And so this is a very simple method. And I think that there's a lot of room for incorporating more domain knowledge to really boost these results. But this is just quickly with the graph platform, what we could do in a few months. And so, yeah, here's a little bit more information. See the leaderboard. We were the best by a considerable margin on some of these data sets. Here we're getting, 0.7 lift in rock AUC. Yeah. And so that's pretty much what I wanted to talk to you guys about today. The key takeaways is just that when you represent your data as a graph, it unlocks this powerful representation that you can use to merge data sets together, to break data silos, to have one unified representation that allows you to really infer some novel things. And yeah, if you want to do this, like for the scale, if you're going to combine data sets, it's going to require some kind of distributed graph platform to do this. That's it. Thank you guys so much. Any questions?
Great, thanks a lot, Andrew. Any questions online or here? Oh, yeah, Bola, yeah, go ahead. Yeah, feel free to unmute yourself and ask a question.
Yeah, thank you so much for the presentation. I'm very interested in the topic. Actually, currently I'm doing my PhD research related to this knowledge graphs in the context of the drug bioactivity predictions as well. So it's very interesting for me. I have two main questions. The first question, when you speak about the node classification part, do you mainly use the semantic information to do this kind of classification, or do you use the similarity, or what kind of input do you have?
It really depends on the data set, the task. In the case that I described with our SimGCN method, we're not using any semantics of the graph really. We're just using these fingerprints as our initial features here. We do have, there's plenty of other tasks where we do use more meaningfully semantic information, but I don't have cheminformatics examples to show you today. But I'm sure they exist. I would like to work with people who have more domain knowledge. I think one of the most exciting places as a computer scientist right now is that I know all these methods, but I don't know what they're good for. And so I need to talk to domain experts to find that stuff out.
Yeah, my second question very quickly. I want to understand what's the differences between Katana graphs and, from the other side, Neo4j with the RDKit plugin.
Yeah, so I can't say that I know that much about the Neo4j RDKit plugin. What our RDKit plugin does, I believe that theirs doesn't, is this indexed substructure and similarity search. And in general, their product is more geared toward being just a graph database, where our product is a comprehensive analytics, machine learning. We're less focused on just the database part of it.
Okay, thank you.
Yeah, that is right, because that would have been my question as well. Also, if we contrast that with Neptune, for example, right? Because the analytics parts and the, I mean, it's focused on the database part, right?
Yeah. With Neptune, for a whole graph pipeline, it involves shuffling a lot of data between all these different AWS services. You're going to send it to SageMaker. It's going to do its DGL thing. I think the advantage with Katana Graph in a production environment is keeping all the data in one place where you're doing analytics in the exact same place that your database is. Really unlocks a new level of speed here. But I would say Amazon does have a great product for this still.
Yeah. Okay, great. Thanks, Andrew. Yeah, yeah, questions as well. Yep.
Hi, Andrew. I'm working at Frederick National Lab as in Atom team. So we are interested in screening multi-million targets. So for molecular property prediction. My question is, what is the highest number of nodes you handled, and what is the speed? Like, do you have, I have seen one slide for speed up, but do you have any comparison metrics with?
So that was a comparison just with the non-distributed PostgreSQL.
Yeah.
That's the number I have for that. And that was on Kemble, which has 2.3 million compounds, I believe.
Mm-hmm.
We have done testing with, I believe, PubChem or something like that, which has 50 million compounds. I don't have performance comparisons for you today for that. Yeah.
No, did you compare with any other graph databases like Neo4j? How much speed up it is?
Oh, I did not. I know that other people at our organization did. I don't have those numbers. Yeah,
Okay.
I don't know the answer to your question.
Okay, and is it open source? Can we just try to download and use?
So the SimGCN thing I showed, there's an open source implementation. Katana also has an open source repo, but what you will get open source Katana is just single machine. We make you pay to get the distributed version.
Thank you, thank you. We are interested in this. So if you can share the slides, and probably it will have contacts of you. So
yep, absolutely.
In future. Yeah.
Yeah, just send them to me. I will put them on the website as well. Yeah.
Cool. Thank you. I absolutely will send them.
Thank you. Thank you.
Okay. Yeah, there's a comment actually from Pierre and seconded by Bola as well, that Neo4j also has quite a powerful graph analytics library. So thanks a lot, yeah, Pierre and Bola for that as well. Okay, yeah, Chris Swain has a question.
This looks really interesting. I'm just wondering, often you get told, you know, this compound is likely to be a hERG inhibitor or whatever, but many of these models don't explain why. Is it easy to gain some insight into the reasons why something's been flagged as active?
You're kind of asking the wrong person for that. I come from like a pure math background, and to me the idea, like, they come out of machine learning models, which we don't have a lot of visibility into. There are lots of methods out there, and you can look to see if their definitions of an explanation satisfy you. In my opinion, in machine learning, there are not really a lot of satisfying notions of explanation, so it isn't something I've done a lot of research into. But we do have at Katana implementing these explanation methods like GNN explainer and stuff like that. But I don't think that my issue is I don't think that they would give you intuition about the real domain knowledge that you need, you know, why we think that this might be a hERG inhibitor or not. It's just going to tell you some graph stuff that if you don't know how the model works, it's not going to help you anyway.
Yeah, thanks. And also with chemical data sets, you have to be careful with biases. Yeah, you have quite a lot of analog bias. Yeah, so even if you want to explain, quite often in practice, it doesn't work as well. Yeah, and it's just a warning as well. Yeah, there was a second comment from Henriette. Or no? Yeah, Yeah. Okay. Very good. Any other questions? Final questions online or here in person? Okay. Great. Then let's thank Andrew again. Thanks a lot, Andrew.
Thank you very much for having me.
Okay. Very good. And we will then come to our in-person presentation. Sophia, yeah, I'll just share the slides from you. So let's see. Share the application. Oh, this one. Here's that one. Oh, no, it was actually. Okay, very good. Okay, I think. Okay, very good. Yep. Yeah,
Amazing. Yeah, it works.
Just to be sure. Yep, I think that looks good.
Yeah.
Okay, so you can hear and see the slides as well online. Yeah, is that right? Andrew, could you just confirm? Oh, okay, that means yes. So, okay,
We
if
can
you
see the
cannot
slides.
it, yeah. Okay, very good. Okay,
Can you hear me
excellent.
as well?
Sophia.
Yeah. Okay. Hi, everyone. I'm Sofia Bariami. I'm one of the postdocs in Cresset. And today I'm going to talk to you about an algorithm that we have developed in Cresset that helps us accelerate and have more robust results in free energy calculations. So first of all, why are we running free energy calculations, right? Many times we want to calculate the binding affinity of a ligand to a protein, so how strongly the molecule binds to the binding pocket. However, in order to do this computationally, it's quite expensive, it's quite difficult to do and error prone. Sometimes though, we're more interested in, we have a ligand, we have a second ligand, which of the ligands binds more strongly to the protein? So what's the relationship between their binding affinities, right? So with the magic of thermodynamics, we can use the thermodynamic cycle we can see here. And instead of calculating the processes, the vertical processes, so the binding affinity, the delta G, we can calculate instead of calculating the horizontal processes, we calculate the vertical ones. And this is because free energy is a state function, so we don't care the path that we're taking in order to end up to the end states. All we care about are the end states. So the difference in the binding between the two ligands is actually the difference in the two vertical processes. So what we do actually is that we take molecule A, we transform it to molecule B. So if you see molecule B has one more chlorine, and then we do this process twice, once in a water box and also in the binding pocket of the protein. So in Cresset, we have an algorithm that does a few calculations. We're collaborating with Julian Michel at the University of Edinburgh. So Julian, they're doing software development using open source software. And then we are actually on the top of his legacy, we are getting the software. And then we make them more user-friendly, we make them more robust, we add the graphical user interface, and then we make it available through our software that is called Flare. So in order to do this transformation that I mentioned before, so transform molecule A to molecule B, the question is, how are we going to do this transformation, right? Because in order for thermodynamics to work, the two states need to be very similar in order for this calculation to converge rapidly, right? And the question is, how different are allowed these two systems are allowed to be? The problem is that even if we want to add a single atom to do the transformation, this difference is quite big. So unfortunately, we cannot do this transformation in one step. Luckily, though, we're not limited by the real chemical space. So what we can do is define a lambda value that can take values from 0 to 1. So if lambda is 0, then I am in molecule A. If lambda is 1, I'm in molecule B. And in the values that lambda takes in between, then we have these alchemical intermediate states. These are states of the molecule that you cannot make them in the lab, right? They are unphysical. And that's why these calculations are also called alchemical free energy calculations. Whereas in these intermediate states, we have a bit of molecule A and a bit of molecule B. So for example, if we have for lambda 0.05, we have, for example, 95% of molecule A and a bit of molecule B. The good thing is that since this neighboring lambda values are so close to each other, the molecules are also quite similar. So the thermodynamic calculations can actually converge. So we go very smoothly from A to B using these intermediate states, and I can actually calculate the free energy in the neighboring lambda windows, right? So by adding all these small delta G's together, I can get a very good estimate of transforming molecule A to molecule B. So this is what I was looking for. So how exactly are we doing this transformation? The thing that changes is a part of the molecule, right? So usually the common substructure of the two molecules remains the same. And then the group of molecule B, for example, slowly fades in, whereas the group of molecule A that does not exist in molecule B slowly fades out. And this may sound a bit hand-wavy, but it's mathematically proven, and it actually works very well. Oops. Right. So the problem is, okay. So the problem is that instead of having one long calculation, instead I'm having, let's say, 20 small calculations. And it's for its state, for its lambda state, I'm running one molecular dynamic simulation, usually of 4 nanoseconds. So the problem that arises here is how many lambda windows do I need to use for its transformation? Because I need to have enough lambda windows in order to have a nice convergence, right? But at the same time, not too many, because then the computational cost is going to be huge. So this is the question that our algorithm is trying to answer. What is the optimal, let's say, number of lambda values that I can have in order to have a good estimation of the free energy that is also not computationally expensive? So the phase space overlap matrix is something that really helps us with that. So let's assume that we have this transformation and we have this link. So I'm transforming this ligand, the first one to the second one. In order to get an estimation of whether, in order to have an indication of whether the estimation of my free energy is going to be correct, what I should look at is the probability of finding a state of, let's say, a state of the molecule in lambda equals to 0 to the neighboring lambda as well. I need to have enough overlap between the neighboring lambda windows. So this matrix actually shows the phase space overlap between adjacent lambda states for two ligands that are connected by a link. So for two ligands that I'm having transformation. And the maths are a bit nasty, so I'm not going to go into details, but if we look at the matrix itself, the interpretation is very easy. So the off-diagonal elements that we see here actually represent this probability of having the states for the specific lambda window in every other lambda window. So for example, the one that I have indicated here with an arrow, it's the state of it's the probability of having a state of the first lambda window in the second lambda window, for example. And this is a probability of 1%. So usually we're happy if this probability is around 0.03, so 3%. If it's 3% or more, then we're very happy. the estimation that we're going to have about the free energy is going to be very reliable. However, if the probability is less than 0.03, then we're going to get an estimation of the free energy, but this is going to be wrong. And not only that, the error is going to be small as well. So I will be very confident that, you know what, this is the correct answer, but it's going to be wrong. So this is obviously something that we don't want to happen. So what happens when there is this poor overlap, right? Usually, one way to improve our results is insert more lambda windows. So since the overlap is small, we need to insert another lambda window in between in order to make this phase space overlap larger. So for example, here we see the two overlap matrices for the same transformation. On the left, you see that with 9 lambda windows, we have quite poor overlap. However, if we do the same thing with 14 lambda windows, we have a very good overlap. However, the problem here is that we cannot insert lambda windows in the first simulation. We need to discard the first simulation and rerun the link. So this is quite annoying because imagine you submit your simulations on a Friday evening or afternoon, whatever. And then you go on Monday to get your results. And then you find out that some of your links have not worked. Maybe there's a poor overlap. You need to rerun the whole thing. You need to go there manually, inspect the links and decide which ones you need to rerun. So this is a waste of computational power. This is a waste of your time. And the modeler itself needs to go there and change. So it's not automatic at all. So someone may ask, why can we just add extra lambda windows in the areas which are problematic? And the problem here is the algorithm that we are using to calculate the final binding free energy, because we're using the multi-state band acceptance ratio, or M-bar. So M-bar requires the energy at state lambda I to be calculated for all the other states. So I need to know all the values that lambda takes before I start. So for example, if I am at lambda 0, then I'm going to calculate the energy at every snapshot for lambda 0, lambda 1 equals 0.1, 0.2, and so on until 1. So I need to know from before all the values that lambda is going to take. What if we just assume that lambda takes some values with like a shorter step, let's say 100 values? And what if I don't use all these values initially, but calculate the energy in these values and just run 10 lambda windows, let's say, so I can have the option if I want to add the lambda window afterwards, right? If we do this, we slow down the calculation a lot. So if we stop every 100 picoseconds, let's say, and calculate 100 energies every single time, instead of 10, this slows down the calculation by 50 to 100%. So this will take twice as much. So it's more or less the same than adding the same number of lambda windows, for example, as we did here. So this doesn't work either. Another thing we can do is store the trajectory files and then go back and recalculate the energies. But at the same time, trajectory files are quite heavy. People don't have enough disk space to spare, so this is not a good idea either. So in Cresset, we have run a lot of FEP calculations, and here are a couple of things that we found out that actually helped us develop the algorithm. So if you remember, we have the transformations in the free and in the bound state. And also we have what we're doing usually is transformation from A to B and from B to A. So doing that both in the free and in the bound state, you end up with 4 overlap matrices. What we found out is that actually the matrices both for the free and the bound state are quite similar to each other. And what we preferably do is run the free system because it's quite smaller than the bound system, since the free system is just the ligand in a small water box, whereas for the bound case, we have the ligand bound to the protein and also solvated in a larger box of water, right? So just by running a calculation for the free state, you can get an indication of how the overlap matrix will behave for the bound state as well. Another thing that we noticed is that the overlap matrix converges very, very fast. So instead of running the usual 4 nanosecond simulation that you would run in order to get all the sampling you need for the free energy calculation, only by running 50 picoseconds, for example, you can get a very good estimation of how this matrix is going to look like. So at the end, what we have, we know that the overlap matrix converges very, very fast. So you can just run 50 nanoseconds. You can 50 picoseconds, sorry. You can also run just a free simulation. So by doing this, you can get a very good indication of whether your matrix is going to converge or not, and whether you will need to add more lambda windows or not. So this is how the algorithm works, more or less. So we set up at first a system with 100 lambda windows. Of course, we're not going to use all of the lambda windows from the beginning, but we initialize 9 equally spaced lambda windows from 0 to 1. And then we run a really short simulation for the free state, just 50 picoseconds. And we compute the overlap matrix. Then we need to check whether it has converged. If it hasn't converged, then we need to find the gaps and insert new lambda windows and repeat the process. As we see here, still there are some lambda windows that the probabilities are still probably less than 0.03. So we need to add more lambda windows here until it has converged. Now, here, keep in mind that we are not running an FEP calculation. We're not using the M-bar algorithm, and this is why we're actually allowed to insert the new lambda windows there. So all we do is that we just calculate the overlap matrix to see whether it converges or not, right? Another thing is that the calculations that we've done so far, the simulations for its lambda windows are very, very they are good. I mean, we don't need to rerun these calculations again. So every time that I'm adding a new lambda window, I'm just running a new calculation just for the window that I added. So at the end, I can discard the results because I've been running all these calculations, but since they are so short, they're not more than like 1 nanosecond. So it's what I need here is just the information of what the lambda vector is going to look like. What are the values of lambda that I'm going to use for the FEP calculation itself. So at the end, you will have something that looks like that. You see that obviously you don't have equally spaced lambda values. There are some places where the lambda windows need to be spaced more like closer together. And this is because the properties of the ligands change quite rapidly there. So I need to be more careful in order to have like good overlap between the different states. Whereas there are other areas where you are allowed to take larger steps. And this is actually the optimal lambda vector that you can have. So it's like the minimum number of values that you can have in order to have good convergence in your matrix. So in order to test our algorithm, we use the famous Wang et al. Dataset. This is a dataset that consists of 8 proteins together with some ligands. So a lot of groups have done FEP calculations, so you can run with your software, for example, compare the results. So what we did is that we ran FEP calculations with FLAIRS 4. This is version 4, which didn't have this this algorithm that I described, and we also run the calculations with FLAIR 5 that has the algorithm, obviously. And here we see the total number of windows. So in all cases, you see that Flare 5 uses 66, 67% of the windows that Flare 4 used. And keep in mind that what you see here for Flare 4 is the final windows that we ran. So obviously there were links that were a bit poor, so we ran them with 10 Lambda windows. It didn't work, so we throw the calculation in the bin. We rerun with 15, didn't work. We rerun with 20. So here what you see is just the 20, let's say, windows. So in reality, the orange bar should be higher. So what you're like winning here is probably like 50% of your time. So this shows that you accelerate the calculation a lot, since you're not running that many calculations. In terms of accuracy, there is also an improvement of accuracy in some cases, especially if you see the PT P1B and the one next to it, P38, we see that we also fall below the 1 kilocalorie per mole threshold. That is the allowed threshold for free energy calculations, for example. So in general, you also improve the accuracy. You see some links, some proteins, I'm sorry, where the accuracy of Flare 4 is better than the one of Flare 5, because what you see here is the mean unsigned error. But I think this is because when you manually interfere with the Lambda windows, you can actually, you can be more precise, let's say. So maybe, there are some cases where there were probably some larger errors in Flare version 5. So to sum up, our algorithm does a fast pre-calculation that can guide the determination of the optimal set of Lambda values. Here on the right, you see a screenshot from Flare with our software. You can see, for example, can you see the mouse? I don't think so. Yeah, okay. So for example, this link here, we just used 9 Lambda windows. So this was like an easy one to run. However, you can see that here, this link, we needed 16 Lambda windows. So this was probably a bit more difficult, I guess. So you have an overall reduction of 30 or more in amount of computation required. So this saves you time, this saves you money. And also you have a higher throughput. So for example, instead of running, I don't know, 50 molecules, now you can run 75, let's say, at the same time. And also you don't have loss of accuracy. This new algorithm is implemented in the standard, in Flare version 5, which is the one that we're using now. And obviously it's going to be standard in the next versions of Flare. So Flare version 6 is coming out in a couple of weeks. So this is included there. Of course, you can bypass it if you want, but this is not suggested. And with that, if you find these things interesting, and if you would like to learn about our webinars and presentations, if you want to read our newsletter with tips and tricks of how to use our software, you can subscribe to our newsletter by following this link. And with that, I would like to thank Dr. Mark Mackey, who is a Chief Scientific Officer in Cresset, and he has worked a lot on this algorithm. Of course, the application science team in Cresset. Thank you, Andreas, for organizing this meeting. And I'm happy to answer any questions that people may have.
Great, thanks a lot, Sofia, for your presentation. Are there any questions here in the room or online? I've seen already, there were a couple online. Mm-hmm. Let's see, maybe let's start with those. Okay, so was actually, I think, previous discussion. Yeah. No, there was a discussion ongoing. Are there any questions or comments for Sofia? Yeah, please. No, second. Oh.
Thanks very much. Thanks very much. I think you explained a very complex topic very clearly. My question is, for very similar molecules, will the optimal schedule be very similar also? And if so, does that mean you can just try and reuse?
Yes and yes, but either way, the algorithm is quite fast. So I wouldn't try to interfere and use the same lambda schedule for the same similar molecules, even they are quite similar, just in case something goes wrong and I need to rerun the link.
Thank you.
Great, thanks. Yeah, Roger, please.
Have you tried using the number of lambda steps you get to change the low map topology you used? You showed, for example, in your set of cycles you were trying to use to cover your set of compounds.
Yeah.
There are some bad links that required 19 steps and other links that required only 9. And clearly it's like, well, if you can very quickly work out the 19 cheaper steps to cover the same compounds with different sets of calculations, seems like a way of improving the set of compounds rather than the lambda windows in just one edge.
Right, but yeah, that's true. But if you really want to include these compounds, then I guess that you will need to. Are you talking about?
So you showed, for example, when you have a set of compounds, go back to the graph which had then the number of lambdas you used in different places. So it's following on from Noel's question. There were 2 compounds that were fairly similar, and so therefore the number of lambda steps you needed to join those together. For people in the room, the bit that was covered over is that for a set of compounds, every compound has to be connected but in a cycle, so that you can do a free energy. But there are different ways for linking those together where you can guarantee they're all in a cycle.
Right, yeah.
You know that the 19 edges cost more than the 7 edges. So in theory, you could then divide that topology or move links around to reduce the amount of computation you have, because your lambda count has told you how expensive it will be.
That's true, yeah. But again, the graph is also generated automatically.
Yes, but it's using Tanimoto fingerprints. The way it's put together like that doesn't take into account how expensive the computation is. You've now managed to work out the weight on each edge. And so therefore the optimal schedule should use your numbers in choosing what the graph should look like.
Great. Yeah, thanks, Roger. Any other questions for Sofia? Oh yeah, please.
Nice talk. So is this single topology, and are you doing the electrostatics and the van der Waals at the same time, or would the optimal lambda spacing change if you started to decouple the 2?
Yeah, so what happens is that the maximum common substructure stays the same, and then you just modify the charges and the van der Waals interactions of the 2 groups that either fade in or fade out. But at the same time, these 2 groups do not interact with each other. So they're not like classes in the simulation.
You can separate out you can do the electrostatics first, and then all the van der Waals, and then the electrostatics again, or you can do everything simultaneously, and it can give you there are different ways that you can turn the groups on and off, which might also affect this a bit, I think.
Yeah. I think in a single topology, though, we first turn off the van der Waals and then the charges on the
Great. Thanks. Let's see if there are any other questions online. Otherwise, let's thank the speaker. Okay, great. Okay, thanks. Let's thanks, Sofia, again. Thanks, Sofia. Okay, very good. So that nearly concludes the day, but that was the fun of science and now the fun of going into the pub. So please join us here going into the Penton Arms. And if you're online, please stay online as well. I'll put you into breakout rooms. So maybe you live in a pub, then you can order a pint as well. But otherwise, go to the fridge. Okay, and join us again September and November then. Okay, thanks a lot, everyone.